Hi, I'm Dr. Makevich, and I'm going to be taking you on a video tutorial walkthrough of Lab 12, Small Worlds.
Before beginning the lab, there are two lithographs from NASA, one on asteroids and one on Kuiper Belt and Oort cloud objects. Um, you should open these. I suggest opening them in a new tab so that you'll have them to refer to after you've read them and when you're doing the lab itself, because they have some answers you might want to use in the lab. But before you begin the lab, you should review some of this information on asteroids and on Kuiper Belt objects. And minor bodies in the solar system are loosely divided up into two general classes. There are rocky bodies, and then there are icy bodies. And the rocky things are everything that's too small to be a major planet, um, but is fundamentally mostly made of, you guessed it, rock. And the asteroids, that's mostly them. Kuiper Belt objects and Oort cloud objects, and also comets, are examples of the icy class of object, where they're mostly ice and not so much rock. And that's why when comets get inside the orbit of Mars, they'll start to develop a tail. So these are the two basic classes in terms of what they're made of. But actually, minor bodies are actually divided up into many, many classes of different kinds of objects with different origins. And if you took Astronomy 111, um, we did discuss that. There was in one of the chapters we went through like 12 different kinds. This lab is actually mostly concerned with three kinds of minor planets, or three areas where they originate and tend to hang out. So when you're looking at question 2 here, they're asking you where in the solar system would you find minor bodies? And honestly, there are small worlds just zipping around all over the solar system, but they do tend to clump in certain places. So there are a couple of key areas that we'll talk about shortly, where most of them congregate and hang out. We're going to be mostly concerned in this lab with the three major classes of near-Earth objects, the main asteroid belt, and the Kuiper Belt. But there are dozens of other smaller classes like the Trojan asteroids and the Centaurs and the trans-Neptunian objects and Plutinos, and they all have some of them have quite creative names like that. But the most of the junk, as it were, the small things that aren't in a planet, hang out in these three major areas that we're going to discuss in this lab. The first question, however, asks you about general kinds of things that you find in the solar system, not just minor bodies. And here's a hint. When answering this question, only one of these things does not belong in the solar system. Everything else, we find at least one example of that in the solar system. One of these things definitely is not like the others and is much, much larger than the solar system and could not possibly fit inside it. To begin the activity itself, most of the activity centers on this simulator, which is this is produced by the ETX lab at ASU. And this is part of the Infiniscope education project. This one I would not only suggest opening in another tab, I would actually suggest breaking the tab out into its own window, so that you can pop easily between the screen with the exercise and your lab itself. It says exploratory mission, your mission if you choose to accept it. That's a Star Trek reference for those of you who aren't Star Trek nerds. It's not my fault. I'm actually a Star Wars nerd, so that's not my particular nerddom. Anyway, it's not an option. You have to do this. I'm really sorry. Um, some students actually enjoy this. I actually enjoy it too. It's a little bit like space Pokemon. Other students don't like it because it is very fussy. Um, and annoying sometimes. And so that's why I'm doing this tutorial, so that you'll get the hang of it faster. And it is a little bit like a video game. So basically, you're going to go through all these steps, and as you're going through, there's a training exercise in the Affinoscope lab. As you're doing the exercise, you should be answering these questions. So we'll go through the test object sections of the training. And once you've done the main part of the exercise and you started collecting your Astro coins, that will open up the videos at the end, which will allow you to on to the main activity. So to begin the main part of the lab, you're going to need to get the Infiniscope thing set up and go through the training exercises. So first you need to click accept, and then a video will appear. This is an introductory video by Lindy Elkins-Tanton, who is the director of the School of Earth and Space Exploration. She's also the principal investigator of the Psyche mission, which is a mission to the asteroid Psyche, which is the only asteroid we know of that's made of solid metal. So it's actually kind of fun and cool, and I'm excited to see what happens when they actually get there, which is a long time from now, many years from now. You should watch this. You also have the option to hit watch later and then click next. Do not at any time hit your back button in this browser or refresh or restart accidentally, because you will lose all your work. I've already done that once and was sad. And you'll have to go through this training exercise again, which is actually quite annoying. So don't hit back. So you're going to hit next, and it's going to take you through a couple of really basic tasks. First of all, you have to demonstrate that you're able to click, grab, and move the screen around. Once you've done that, it will let you proceed to the next training task. So now it gives you this little map down here. And this yellow orangey area is the part of the Earth's orbit that you're looking at. So the Earth, as it approaches, and it's in its orbit, as it approaches the yellow area, it will appear on the screen. And now we have been directed to chase it, basically. And after you've clicked on the Earth, it will then prompt you to find 3 other planets. Now, planet is, of course, the Greek word for wanderer, and planets are basically things that move against the background star field. So you're going to, honestly, holding still is not a bad strategy, because if you see the Earth going through it, you know you're looking at the plane of the ecliptic, and eventually another planet will wander along. This really fast one is Mercury. It's actually quite hard to tag. The slightly less fast one is Venus, and you can at any time hit pause once you see a fast-moving object like this, and that'll help you with catching it, especially with the fast ones. But you need to catch 3, so we'll wait for Mercury to come zipping along again. You can also slow down a little bit, although if you slow down too far, everything will just stop completely. And if you get impatient, or you can just wait for Mercury to come zipping along. Here it comes again. So fast it's hard to click even at the slowest speed. All right. Now we're going to have to wait for a slower planet. Mars, Jupiter, Saturn, Neptune, they're all much slower. So I actually recommend speeding up just a little. That'll help you find them. There's one without a label. All right. So now once you've clicked your 3 planets, the simulation will give you all of the planets. So now we have all the ones, including the ones we didn't actually click on: Neptune, Jupiter, Saturn, all of them. We're now tracking the Earth, however. Our view is moving at the same speed the Earth is. And they're going to ask us to move a test object and match the Earth's speed. So the point of this exercise is that planets that are inside the Earth's orbit, like Mercury and Venus, you'll see them zipping by. That's because they are moving at a faster speed. Because of Kepler's law, planets that are closer to the sun move faster, and planets that are farther from the sun move slower. And so you see them moving more slowly or faster across the background stars. Our point of view is sun-centered. We're currently just standing on top of the sun, presumably burning our feet, watching these planets go by, but we're tracking the Earth right now. So we're going to take a test object. The test object is a blue asteroid-looking thing. And there's another training video where they kind of demonstrate this badly. I'm just going to explain it. So in this little map here of the Earth, you're going to take the test object and you're going to drop it someplace and see if it manages to keep up with the Earth. Now, if you drop it in front of or behind the Earth, you can drop it in front. But if you drop it outside the Earth's orbit, the Earth will move faster than it and it will eventually pass it. And that's not what they want. They actually want you to match the speed of the Earth. Apparently, we need to download the goofy video. Hang on. So you're going to want to take your test object and you want to keep it inside the yellow arc. And you want to, if you put it at, they want you to match the speed of Earth. So you're going to need to put it somewhere near the Earth's orbit so that it's kind of keeping pace with the Earth, not moving ahead of it, not moving behind it. So we're going to check the speed. Yay, we did it. Now they want us to drop the text object so that it's faster than Earth. That means we're going to have to put it inside the Earth's orbit somewhere and then check its speed. And then they want it to be slower than the Earth, so that means putting it somewhere well outside of the Earth's orbit and then checking its speed. Right. Now we're free to actually start the exercise once we've passed this. Again, if you make a mistake and hit restart or hit back or any of those things, you will lose your progress to this point and you'll have to do this training exercise again. So to try not to do that. So we're going to look for a small object. And so you see a whole lot of things that aren't planets that are moving through my field of view. And so even though a lot of people don't like this exercise because it's kind of fussy and kind of like a video game, I actually really like it because it's actually a bit like actual astronomy. This is actually what asteroid hunters do for a living. Oh, here's something really slow. Move over there. I didn't go the right way. And it's that they basically sit there and watch little tiny dots moving against a background of other little tiny dots. You see how slow Saturn's moving? So it'll give you an alarm if you sit here and explain things for too long instead of clicking on the objects like you're supposed to. So they want you to click one of these moving objects and you can try to catch them while they're moving or hit pause if that's too tricky. Now we're going to, once you click on it, it will track it. It'll keep it in the center. And now you have to use the test object again to determine what distance from the sun it is. So again, if you put the test object in the field of view and it's much faster than the object that you're tracking, then you need to move your test object further out. If you put the test object in your field of view and it's slower, then you need to move it further in. So this object, I've run out of field of view actually, so I need to zoom out a bit so that I can put it out in the outer planet somewhere. So I'm going to take my test object and put it out here where Jupiter is. And now finally I'm moving slower than my main small body. So it's somewhere between Mars and Jupiter. Okay, I think we're kind of close. How close do you need to be? That's an excellent question. I'm not really sure. I think basically you need to be between the two relevant planets. So anyways, once you've successfully matched speed, so you know you definitely have determined that in this case this object is between Mars and Jupiter. Now you've got a probe, quote unquote, that you've launched, and so they've given you a little 3D simulation of your asteroid, and you need to search the surface of it for the little blue dot, and you can zoom in more if the blue dot is too small for you to click. You click on it, and it will give you a coin. It will tell you what object you've found. In this case, you've discovered Vesta. So you've actually I have discovered the second largest asteroid in the asteroid belt. And if you check your cache case, it'll tell you how many of each kind of coin you have. In order to finish this part of the lab and proceed to the next part, you're going to need to get 3 kinds of each type of minor body. What's the difference? You need 3 of these, 3 of these, 3 of these. The difference is that asteroid belt objects you're going to discover as you use your test objects are generally, let's click out of here, they're generally going to be, asteroid belt objects are going to be between Mars and Jupiter, and they tend to move slower than Earth. Vesta here is moving slower than Earth, but a lot faster than, say, these outer planets like Saturn, Uranus, and Neptune. Meanwhile, over where the Earth is, you see this object that's chasing after it? These guys are moving at about the same speed Earth is. Those are almost certainly near Earth objects. They're moving at the same speed as Earth, so they're probably at close to the radius of the Earth. So to see them, we'll have to zoom in. We'll start playing. We'll drop our test object. Look, it's really close to Earth, so if you put a test object near Earth's orbit, it tracks it really well. Test. So here's our little cache. Again, it's easier to zoom in. Click on it. And lo and behold, we have discovered a near-Earth object, an NEO. And so now we have one of these coins. The hardest coins to get are the Kuiper Belt coins, in my opinion. So how do we find them? They're very slow. The problem is that at normal speeds, we'll see the near-Earth objects zipping by, and the asteroid belt objects kind of ambling by at a reasonable speed. But the Kuiper Belt objects are so slow that you won't see them pretty much at all. So I strongly recommend, they're slower than Uranus, they're slower than Neptune, so I strongly recommend speeding the simulation up all the way. And then watching, you may have to scan the sky a little bit. Because you're looking for something that even at top speed is still moving really slow. There's Neptune, looking for something going about that speed. And this is why they're hard. There they are. There's one. So this little creeper right here. All right. Now, to match speed, again, we're going to need to zoom way out. So we know this thing is moving slower than Neptune, maybe even. Let's see if that did it. No, a little farther out than that. Not bad. Okay, test. And ta-da! So we found our first Kuiper Belt object. I'll have to zoom in a little to get that. These caches are a little finicky as well. And we have found a thing that's called 2014 MU69. I don't know. And we have one Kuiper Belt object. So again, you're going to need to get 3 Kuiper Belt objects, 3 near-Earth objects, and 3 main asteroid belt coins in order to continue. So I'm going to go to do that. So now I have finally, at long last, gotten my 3 Kuiper Belt objects, and I've got 3 of each kind of coin. So now I'm able to click out of the cache, and now finally the map button has appeared. But before you can click on the map button, you're supposed to look at the actual map. And so what they want you to do is to pay attention to the orbits of the objects you found. So you found 3, you can find up to 5. The Kuiper Belt objects' orbits will appear as orange arcs, and you can see where they are located relative to the planets. And as you go inside, you'll notice where the green arcs are located, and those are the main asteroid belt, MABs, like Vesta and Psyche and Sirius. And then as you go in further, you'll see the yellow arcs, which correspond to the near-Earth objects. So you're supposed to take note, basically, of which planets these different kinds of asteroids or Kuiper Belt objects are among or between. And then once you've made note of, between which orbits these things tend to appear, then you can go on to the next part of the exercise. And they will ask you to place a beacon in each one of the 3 zones that you have observed these objects in. So, for example, if you think you found all your Kuiper Belt objects between Uranus and Saturn, by the way, you didn't, you could put a beacon here and then verify it. And then because that's not a good place to put, and in this case, it's actually asking you for near-Earth objects. That's not a good place to put them. You have to try again. So don't forget you can zoom in and out. So if you want to say your near-Earth objects are, I don't know, near Earth, then you could try that. And it will tell you what the zone is. So you'll have to complete that. And you'll want to remember your answers because they will help you with some of the following questions. Once you've placed the beacons in all the correct places on the map, the main screen of the Small Worlds Infiniscope will give you a button in the center that says Finish. And you can then hunt the rest of your Astro coins if you are so inclined, or you can click Finish and just get out of here. But before you hit Complete, you'll be given this screen of interesting links on the images and videos and shape models that you saw in the astro caching exercise, but also these really critically important videos and links on near-Earth objects, asteroid belt, and Kuiper Belt objects. The near-Earth objects link, if you click on them, includes a video by Phil Christensen, which you will need to watch in order to answer this question. The links on the side are also important. You'll need to click on them in order to learn about the OSIRIS-REx mission, for example, which is a question. And again, very important, when you are done watching Phil Christensen talk and clicking on these links, do not click back. There's a little X up here. You want to click that to close that window. Again, if you click back, you risk losing all the work that got you to this point. Don't do it. You click on the main asteroid belt, and here's a video by Eric Asfog. Stuff on the Dawn mission. Point of interest, the question asks about the Dawn mission, and it asks you which of these asteroids Dawn explored first, and then it moved on to explore which of these other asteroids. And the sad fact is that it is not now exploring. It was, as of a few months ago, it was exploring one of these asteroids, the second asteroid, but now it's kaput. It actually, the mission ended, the satellite orbiter probe, it died a few months ago. It was actually pretty recent. So Dawn is actually over. And Kuiper Belt, we have a video by Minnie Wadwa from the Center for Meteorite Studies. and she's going to talk about the Kuiper Belt, and you should click on the New Horizons mission, which already visited Pluto and is on its way to a true weird little tiny Kuiper Belt object, which is completely unlike anything we've ever explored before. When it visited Pluto, that was actually really exciting because we had no idea what it looked like, and it completely surprised us. So stay tuned, because New Horizons is still zipping out of the solar system as fast as it can, and it's en route to its final target. So that's something exciting that's going to come up in the next year or two. And at this point, now, once you've answered all these questions and gotten down to here, now it's probably safe to actually hit complete and exit out of the video. But first, you want to answer this question about which areas of the solar system did we indeed find the majority of the small worlds to be located in. And there are 5 options. You're going to want to click on 3 of them. So you'll want to have 3 of these options clicked. They're going to correspond to those 3 main areas you placed beacons in. So 3 radio buttons clicked, and then you can proceed to the last section of the lab. So for the last part of this lab, we're going to look at the speed that those small worlds are traveling at. So you will have noticed during the astrocaching exercise that some of the objects you were chasing were moving much, much faster against the background sky than others. And some of them were moving very, very slowly. So everything in the solar system, including the minor planets, everything follows Kepler's law. And so comets, asteroids, just like major planets, they all follow Kepler's law. So if you're closer to the sun, you move more quickly. And if you're farther from the sun, you move much more slowly. The Earth itself, we're going to base everything off the Earth. The Earth is going 30 kilometers a second, or 100,000 kilometers per hour, zipping through its orbit. That's not a great number to work with. So for the sake of this exercise, we're going to say that the Earth is traveling at a speed of 1 Earth, just like we have defined 1 AU to be the distance between the Earth and the Sun. We are going to define 1 Earth speed as equivalent to 100,000 kilometers per hour. 1 Earth speed, because it's a nice round number that we can deal with quite easily. It makes the math easier. I'll show you what I mean. So this calculation is going to ask you for a near-Earth object, an average distance of blah AU. I'm not going to actually do this problem for you. I'm going to use a different number. But the general idea, that the little thing you should be checking, is that near-Earth objects are close to Earth, and so they're going to be traveling at something like the Earth's speed. The number that you get should be close to 1. Asteroid belt objects are out there at 2 to 5 AU. They're between Mars and Jupiter, so they're going to be moving at quite a bit less than the Earth's speed. And anything in the Kuiper belt object out there past Neptune is going to be moving at a great deal less than Earth's speed. So we'll just do an example calculation. We'll use something at 2 AU. So if we're talking about something that's just out past Mars at 2 AU, how do we do this calculation? So speed is inversely proportional to the square root of the distance. That's a horrifying thing for me to say. So we're going to take the distance in astronomical units. I'm going to use my example of 2 instead of 1.1 or 3 as we have in the actual problem, but just use those correct numbers in this calculation. I'm going to open up my little Apple calculator. I'm going to type 2. I'm going to take, that's the distance of the small world relative to Earth. Earth is at 1 AU. Small world is at 2 AU. I'm going to take the square root of it. And then square root of it, but it's 1 over. So it needs to be on the bottom, not on the top. 1 over, and that's my answer. My answer, if I were given the question where an asteroid in the main asteroid belt has an average distance of 2 AU, the correct answer would be 0.71. That shouldn't be an answer because I don't actually have 2A. Okay, all right. So you can do that same calculation. And this is one of the few cases where order of operations isn't critical, because this division and this square root, you can do them in either order. So you could do the same thing in reverse. You could take 2, 1 over, and then take the square root, and you get the same answer, 0.71. And then the last bit is about the Oort cloud. You have to do the same exercise, but for the Oort clouds, you're going to do it with 5,000, and then you're going to do it with 100,000 AU. Exactly the same bit of math, 5,000, square root, and then 1 divided by whatever that answer is. If you don't have this handy little 1 over x button, you can do 1 divided by whatever your answer from the square root is, and that'll still work. And then you'll get these answers. And then the question is, based on this information, why do you think it's so difficult for us to confirm the presence of the Oort cloud? So quick word about the Oort cloud. The Oort cloud is the other major area where comets and minor planets hang out. And we know almost nothing about it. The only reason we really think it's out there is because of the existence of long period comets that come in on nearly hyperbolic orbits, and just sort of jet around the sun once every 10,000 years, and then we never see them again because nobody's alive to see them again later. And their origin point, we believe, is way, way out there, well past the Kuiper Belt. And they come in weird elliptical orbits from every which way. They don't follow the plane of the ecliptic. And we have yet to actually find, I don't think we've actually ever found an Oort cloud object just hanging out there because they're far away. So you saw how slow Kuiper Belt objects are. These things are moving infinitesimally slowly. And they're also incredibly faint because they're far away from the sun. So they have very little of the sun's light to reflect. We just haven't found them yet. All we have is the long period comets. So the answer to that one free answer, we haven't found them because they are really far from the sun and they are really, really slow. Okay, at that point you can save and submit.